Hey, what's up, guys? This is Chung here. So today let's take a look at this last problem of last biweekly contest. Uh, Number 1606. Find servers that handled most number of requests. Okay, this is a hard problem. Okay, let's take a look the description of this problem. Basically, we have k servers numbered from 0 to k minus 1. Okay, and then once after the k servers, you're also given like a bunch of the rival request, and the rival time is strictly increasing. Okay, and here we have a like load of each request. Basically, this is like the duration of each request. Oh, by the way, I changed the background of the web page to the white color because we have some there's an image here. Basically, if I still use the dark background, we won't be able to see those kind of those signs here. So and cool. So with those three given parameters, and then now we have a like a assignment rules here. Basically, the requests are being assigned to each servers based on this specific rule. Okay. The first one, basically, if the server is all the servers are busy, then this request is simply gets dropped. Okay. And then if this server is available, okay, basically what do we do? We this is the sequence of the request, and then we just do a mod out of the k here. If the server is available, and then we just simply assign this request to the server. Otherwise, otherwise we just try to find the next available servers. Okay, which means that let's say the free server is like uh, if the current if by after doing this mod here we have three here and the total server is five. So which means that from three to five, we're trying to find if from three to five there's any available servers. If not, then we'll go back to zero and try to find if there's any available zero from zero to two. Okay. You know, actually this is like so I think in the real world, so I mean for the load balancing in the system design, in terms of system design, I think for this is kind of like the load one of the load balancing uh logic. I'm not qu I'm not that quite sure. I think this is something like similar to a round robin thing. Basically, this the first one gets assigned, then the second one. Basically, this is like a hash function, right? And we do a hash function, and we're trying to send this request to this server after hashing. And if that server is not available, we'll just try to find the next available one. Okay. And then it asks you to return the the list of containing the list of servers which who handled the most request. Okay, and this return value could be a list because multiple servers can handle the same amount of requests. For example, the first one here, when the at the time one here, request zero comes in with a load five. So which means server 0 will handle the first request, and then the ending time is 6. And at now the next request comes in at time 1, which will last for 2 seconds or 2 minutes, and which means this request will finish at 5 sorry, at 4. Okay, and and then so on and so forth, right? And then in the end, we simply just return the server that handles the most requests. So this problem, I think, is more like on the implementation side than the algorithm side. So, but there's a few things we need to be careful. First is this. I mean, first is uh, the constraints here. As you guys can see, the k has a like up to 10 to the power of 5. Same for the load and arrivals. So which means that when we try, so which means that our algorithm has to be around n log n. Okay, which means when we try to find the if the current server is not available, it's busy, and we need to find a better way of finding the next available servers. We cannot simply do a loop here, right? Because the worst case scenario, I mean, the worst case scenario is that, I mean, if all the servers are free, that which means that let's say if the current server is four, it's like it's four, right? And then the next available one, let's say is three. How can we find the three after four, right? We cannot simply do let's say if we have 10 to the power of five servers, we simply just cannot loop everything from four to 10 to the power of five, and then if we didn't find anything, we go back to zero, right? We basically we cannot do a linear scan. That will be the time complexity of doing that going to be n square, which will be a TLE. So we need to find a better way of searching this one here. So one way of doing this is that the we have to use like a sorted structure, and actually in Python there's no built-in structure. There's no such built-in structure that can give us the things we need. That's why for this problem I chose to use C++, because in C++ there's like a set, right? There's a set. It's like a sorted list here, and we can simply iterate through it from either from the search the 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 second half or the first half. Actually, I mean, if you guys really want to use Python, I think there's another library in Python where you can import. I think it's called a sorted list. I think that can give us a similar result. If you guys really want to try that, I will also show you guys the in the end of this video how to do it in Python code. But for the main part of this video, I'm gonna use C++ since we haven't. I think I rarely use C++, so it's a good it's also a good practice for me. Okay, so assuming we have set here, basically this set here, right? So we use the set, and the set will be storing the idle. Okay, basically we'll be maintaining like a idle servers list in this set, and as you guys can see, since this set is a sorted one, so basically we'll have a sorted idle servers here, and every time when we have our rivals here, we're gonna try to find the next available server from this idle set. So that's the first thing. And the second thing is that when the next arrival time comes, we need to check which servers can be freed, right? So to do that, we can simply use a priority queue, right? Basically, every time when a new arrivals comes in, we just check if there's mm, any server's ending time. The ending time is equal or smaller than the current arrival time. If that's the case, then we know, okay, this server is not busy anymore. So we can mark this one to the idle one, basically, which means we can just add that server into this idle list. Okay. And to do that, I mean, so when we use the priority queue, like I said, first we need to store the ending time of that request. Okay, basically we're gonna have like a tuples here or a pair in C++. So the first one is gonna be the ending time. Okay, but the second one we also need to store like the server ID associated with this server, so that later on when the request can be freed, and we can just simply use this server ID which we previously stored in this priority queue to to add into this idle. Cool. Yeah, I think let's see. Let me see here. So let's start the coding here, and the first one is C++. Okay, let me remove everything here. So like I said, the first we're gonna have like a two data structures. The first one is gonna be the priority queue, right, which will be maintaining the current, basically the current busy servers. Okay, and like I said, priority queue. Okay, like I said, since we're going to store two things in the priority queue, the first one is the ending time, second one is the server ID. So which means when we define this priority queue, right? So we're gonna have like the priority queue, right? So we will need to maintain two things. The first thing is the we're gonna have a pair, right? So the pair is the int and the int, right? So that's the first parameters, right? And then the second one is the uh, in this priority queue we have a list, right? So which means that's gonna be a vector, also the vector type, right? It's gonna be the same of these things here. The vector time is also store like a pairs in it. Okay, that's the vector. And the third parameter is how are we going to define this priority queue, right? So in this case, we're going to use the greater, which means the second one is greater than the first one, because we need to get the smallest ending time later on. So and we're gonna have like this greater, and we're also gonna have a pair here, right? So that's how we define this priority queue here. And then the next one, like I said, we're going to use like set in the C++ to use the idle, right? So we're gonna store the idle servers inside here. Okay, and of course, in the finally, we will also need like a vector to store the counts, right? So for each of the server, so we're gonna have a vector dot int and a count, right? And the length will be k. Okay, so now we can simply start our for loop here, like the int I in the 0, I smaller than arrivals, right? Arrival dot size, right? And then I plus plus. Okay. So uh oh sorry, I think here, I mean, once we define the idle here, we have to initialize it. Basically at the beginning, all the servers are idle, which means we have to insert all the servers into this idle first. Basically, if I in range, sorry, sorry, I have been using Python for too long. So I equal to 0, I smaller than k in this case, right? And I plus plus. So and then we just simply do idle dot insert, right? We do idle insert dot I, which means so now we have at the beginning every server is idle. So now we have this kind of the rivals, right? Now we have a rival, and now let's try to free some servers, right? So here we're gonna try to free servers. Okay, how do we free the servers? We just do a while loop, right? We do a while loop here. We check, right? First we check if the priority queue is not empty, right? Same thing, similar like how do we check in Python? So first we check if this priority queue is not empty, and what? And the rival, right? And the rival time is 0. It's I. It's equal greater than the priority queue dot top. Okay. and basically the priority queue dot top will give you the first element in this priority queue, and we check if this one, if the current arrival time is greater than this one. Okay, dot first. So don't, since we're storing like two values in this one, the first one is going to be the ending time, the second one is going to be the server ID. So in this case, we're using the ending time to check that. If that's the case, so we need to I mean, first we need to do a pop here, okay? But in C++, the pop doesn't return you the popped item. So it simply returns like a void type. So which means we cannot do the pop first. We have to add this fridge server into the idle uh, set first. Basically, priority queue dot top dot second, right? Since we need that server, since the idle is maintaining the server, the freight server, and then we can do a pop here. Okay. So now we have a valid. So now we have a maintain update our priority queue here. Now we can simply now we have a updated idle server here. Okay. Now we can try to assign the current request to the available server, idle server. So first I'm gonna try to do a s, right? So gonna be a s equals to the I mod k. Okay. So now it's how can we use this the set to find the next available one, right? So we just use this, right? So we do auto, we iterator equals to idle. In the set in the C++, there's like this function called the lower bound, right? Lower bound of s. So what this one does is that basically we find the first index or the first iterator, right? That's is equal or greater than the current s. Okay, and basically if the iterator, right? If the iterator is in the is equal to the same, if basically if we didn't find it, okay, if we didn't find it, it means that we have to start from the beginning, right? Basically we'll try to find the first available servers in this set. So why is that? Because let's say in this idle set here we have a 0, 1, 2, 4, 6, 8, and 9. Let's say we have this list here, right? Oh, by the way, so the data stored in this set is not like this. It's like basically it's a red black tree data structure inside. How how did they how does C++ implement this? But that's not uh, what we're going to worry about here. We just need to know we will need to use this one. So let's say we have a 5 here. Let's say we have let's say this s currently equals to 5. Um, sorry. Mm, I'm sorry. So I think let's say the s equals to 10. Okay. And then we're trying to find the lower bound of this of s in this like set here, which will give us the at the last one. Then we know, okay, we didn't find anything after 10 that is available. Then what's the next available one? So we just need to find the first one. Basically, we just need to find the first element in this set, right? So in this case, it's going to be 0. So how do we do it? We simply do this. We simply do a move the iterator, right, into the beginning, right? Now we have like this the iterator pointing to the beginning of this uh of this beginning, sorry, of this set here, beginning. And basically if now we can simply do a check. How do we know if there's basically if there's no available servers here? We should skip that. So how do we know that? So basically even after we move the cursor, the iterator to the beginning, if this iterator is still pointing to the idle dot end, okay, then we know, okay, all this, basically the set is empty. That's the or we can just do a check in the at the beginning. We can just check if the idle is, I think there's a idle dot size yeah. Or we can in the beginning we can just check if the idle dot size is equal to 0, and then we can simply continue. Or here I'm just using this one, right? Basically, if it's a 0, it means that okay, so at the first time the iterator will be the end of the end, but when we do the begin, it's also basically the idle is the begin and end are the same, right? And then we just continue. This is for the if all servers idle is empty. Okay, so now we have a we check now we have an iterator that's pointing to the available server that we need. We can simply get that index, get the value from it, right? So how do we get the value? So we define a selected, and then we just dereference it, right? We just do a star it to get the value out of this iterator. Okay. Now the next one will be simply we just add these things. We insert, right? We uh sorry. So we're gonna remove it. We need to remove it from the from this idle server because now this one becomes busy. Okay. And also we need to push this one to the priority queue, which is represents the busy servers. Like I said, the first one, right, is going to be the rival I plus load I. That's going to be this request ending time. Okay, and the second one is of course is a selected server. Okay, that's that. And the last step is just simply increase the count of the selected servers by one. Okay. Yeah, I think we can just do a 0 here. We initialize 0 for everything. Cool. So yeah, that's that. And after this for loop, we have all the counts we need here. We can simply do a calculate. We just get the max of the we get the max element, right? Element of the of this count list here, right? So we're gonna begin dot count dot end, basically from begin to the end. And oh, okay. So and remember, careful. This max element is also returning like an iterator, not the value itself. So we have to do this star same thing here. Now finally we can create create our answer here. Okay, and for int I equal to 0, I it's smaller than the k here. Okay, and then I plus plus if the count, right, dot I is equal to the max, right, and then we do an answer dot pushback, right? So we just add this one to the final answer, and then in the end we can finally return our answer here. Cool, yeah. And let me try to run this code here. All right, cool. So this one accepted. Let's try to submit it. Yeah, cool. So success. All right. Cool. So how about time and space complexity, right? So the space complexity, so this one's like the k here, right? So it's, let's say we have a k and a rival, they're all n here, right? So we have a, that's the k here, and we have a, this is n here, right? This is an n here, and we have like the for the while loop here, this is gonna be treated as a constant because we're gonna uh, because each of this arrival will only be push and popped once. Okay, so which means we have like a log, and each time we push this one here, right? And the worst case scenario for both the idle and the priority queue, they're both like k number of elements inside. So which means that for the priority queue pop, right, this is gonna be a log k here, right? And also for this idle lower bound here, this is also a like log k, right? So and here is just and also this push here, right? It's also another log k here, and here is like just another o and k here, o of k here. I mean, in the end, I think something similar to n times log k. Yeah, that's basically the time complexity for this problem. And the space complexity is the I think we have a priority queue here, right? So which will be storing all the 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 requests and servers here. So which means that uh the space complexity is going to be a n times k. Oh, sorry, n plus k here, right? So here's n because we're storing the request here, and the server is k here. So that's why we have a n plus k space complexity here. Cool. And yeah, I think that's it for this problem. Just to recap real quick, basically, the um, the most important thing for this problem, I think for me is to find a proper data structure so that uh, we can quickly find we can quickly find the next idle server for the current request, right? So that's the first, and the second one is the second thing is that we have to use a priority queue, right? Basically, that this is like I think this part is not that hard to come up with, right? Basically, we just need to use a priority queue and to free the servers, right? Whenever there's a new arrival, there's a new request arrives, okay? And other than after that, I think nothing's fancy about that. Just maintaining this idle set and this priority queue. Okay, cool. So that's the C++. And for the Pythons, I'm not going to write everything because I'm going just to show you guys the Python uh, code here. Basically, like I said, the structure is exactly the same comparing with C++. The only few differences. First one is this: we have to import the sorted list from the sorted containers library. And then after that is just like first we have a priority queue, right? And then we have a count, right? And then the idles instead of a set, we're using like a sorted list here. So same thing, we initialize the idles at the beginning, and then we loop through each of the requests. Okay, so we zip this arrival and loads here. So first step is we just try to free any servers if possible. Basically, if the priority queue is not empty and the current arrival time, right, is greater than the first one on this priority queue, and then we just since in Python this pip pop will return the popped item, so we can do a pop first, and then we use the second element, right, of this in this priority queue, and then we just add it. We just do a idle dot add to this sorted list here, and then after that, the same thing. We just do a get the current server ID, and then here is a little bit different than the C++, but in red, but it turns out to be the similar concept here. Basically, similar thing here, right? We're trying to find this S inside. We're trying to use a binary search basically, to find the current seriality in this idle. If the index basically if the current index is the same of the idle's length here, then we know, okay, we didn't find it. Okay, if we didn't find it, then how can we do? We just need to find the first element in this uh idle list here. So the way I'm doing this is basically I'm just trying to find the zero, which means the smallest servers in this index, starting from zero. In that case, we can just simply uh, find the next available index. Actually, you know what? Do we have actually I'm wondering if we have can we use an index of this? I'm not sure actually. So okay, we'll do that test later on. So basically, then we try to find the first element in from this idle here, and then if this index is still the same as this one, we continue, which means there's like nothing inside of the idle here. And after that, we same thing here, right? Because we have this is like the index, right? We're gonna get the actual server ID from this index, and then same thing here. We remove it from the idle, and then we increase, and then we push it to the heap queue, the priority queue, and then later on, in the end, we simply do this. Okay. So let's try to run this submit. Yeah, yes, I think it works. Okay. Yeah, actually, I thought about it. Actually, here, we don't have to do this one here, right? We don't have to do a binary search one more time because here we know, okay, we didn't find anything. Same thing for the other C++ solution here. So after we didn't find anything, after this S here, all we need here is we just need to get the first element in this idle here, right? So we can simply do this. We can simply do if idle, right? If not basically if not idle, which means if this one is empty, we can simply continue, right? And then else index just equal to 0. Okay, we can remove this thing here because we know if there's idle here, and then we just need to find the first one from this idle server, and that will be our selected server if we didn't find anything after this S here. Okay, yeah, this will just work. Yeah, we can do similar thing in the C++, but I'm not going to change it. I'm not going to do it now. Okay, cool, guys. I think that's everything I want to talk about for this problem. And thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.